In today's lesson, we are going to be doing a review of 5.4 and 5.5. We're going to be doing these problems in several parts. So our first goal is going to be to evaluate the integral of sine 4x dx. So my first question to you is, thinking backwards, does it seem like you would need to use a u-sub to take the derivative of whatever the answer is to this question? And hopefully you're thinking, yes, and that's your key to use a u-sub. If you were to take the derivative of a sine, a cosine, a tangent function of 4x, you see that's our baby inside. And so to take the derivative, I would need a chain rule. So thinking backwards, it means that we would need to use a u-sub to take the antiderivative. That's kind of your key to knowing if you need to use a u-sub or not, is if you would need to chain if you were taking a derivative. So let's go ahead and identify the baby. So hopefully you see in this problem, sine of 4x, that 4x is going to be our u. All right, let's go ahead and solve it. Our u is that 4x, meaning our du is going to be, the derivative of 4x is just 4 dx. Now, if we look at this problem, we only see a dx, not a 4 dx. So we want just a dx to be able to replace it with. So let's divide both sides by 4, 1/4 du. We can sub in for the dx. So let's go ahead and make our substitution. This is going to be equal to the integral sine 4x is our u, sine u. And then our dx we can replace with this 1/4 du times 1/4 du. Let's go ahead and take that constant out. And now the antiderivative of sine, is it cosine? Is it negative? Go ahead and put in the cosine and then just think the derivative. The derivative of cosine is a bad sign. So it's not negative, so we need that negative there. With the indefinite integral, don't forget plus c, because the derivative of a constant would be 0, so we need that plus c. We don't know if there's something tacked on here or not. Our final answer, negative 1/4 cosine, our u is the 4x plus c. So whenever we have an indefinite integral where our answer is a function, not just a number, we do want to go back and substitute from the u, go back to the x. That's very important. So only when our answer is going to be a function, so that's an indefinite integral, one without the bounds, then we want to go back and plug in our u. If we're just solving, which we're going to do in a couple slides, then we never need to go back to the x's. I'll explain that more when we get there. So on this next one, evaluate the integral of x root 2x squared minus 1 dx. Hopefully you're seeing what the baby is. If you're not yet, you could rewrite this as the integral of x 2x squared minus 1 to the 1/2 power. And hopefully that helps a little bit because this is definitely our baby. So our u is going to be 2x squared minus 1. Our du is going to be 4x dx. That drops off. It's a constant. Now, do you see a 4x dx here? No, you do not, but you do see an x dx. So we want to isolate just that x dx. That's going to be 1/4 du, divide both sides by that 4, equals x dx. So now we can replace all of that in that equation. So we have the integral that x dx is going to be our 1/4 du. So I'm going to put that on the end. And then this was just our u to the 1/2 power. Okay, I'm going to take the 1/4 out. Integral of u to the 1/2 du. Let that 1/4 hang out. The integral of u to the 1/2, add 1, and then flip it. Don't forget the plus c because it's an indefinite integral. And then I'm just going to simplify and plug back in for the u. So that is going to be 1/6 u, which is 2x squared minus 1 to the 3/2 plus c. That's my final answer. So this is a little note for everyone in class. I just saw a lot of people forgetting the antiderivative of 1 over x dx, and that is ln absolute value of x plus c. So either people were forgetting that formula or they were forgetting to add the plus c. When it's an indefinite integral, you need the plus c. So that's just something you definitely need to know. We're going to see so much of it. And you do need the absolute value because remember the ln function can only take in a positive value, and that is actually an important thing that you have in these questions. We can dig more into that later, but for now, just make sure that you memorize that. Okay, does this one look like a u-sub problem? And it might not immediately, because it looks more like a quotient, right? So I'm saying to you, try to rewrite the integral and then see if it looks more like a u-sub type problem. When I rewrite that integral, I had 3x squared over x cubed minus 4 dx. Couldn't I rewrite that as the integral of 3x squared times, if I bring this up, x cubed minus 4 to the negative 1 power, because it was in the denominator, dx? And if I rewrite it like that, then I think it's pretty obvious what my u is going to be, and I see that my du is probably going to work out pretty nice, because if my u is x cubed minus 4, then my du is going to be this 3x squared dx, which is totally what I'm going for. So now let's go ahead and solve. I'm just going to rewrite it how I had it before. Again, our u was this x cubed minus 4, and our du was this 3x squared dx, which was totally what we needed. We don't need to do any dividing on this one. So now we can replace this 3x squared dx with this just du, and then this is going to be our u to the negative 1. Now, u to the negative 1, you're probably thinking to yourself, okay, I need to add 1 and then divide by what I added. Oh, that doesn't work. You can't divide by 0. And so that is your cue that that's the ln one. That's how I thought about it before it came naturally to me. So this is 1 over u. Antiderivative is ln absolute value of u plus c. Plug back in. X cubed minus 4 is our u plus c. That's our final answer. Now, on this one, again, it might not be immediately obvious to you what the u is. And I think that a big hint when we're doing these sign ones, and I said the same thing when we were doing derivatives, so I'm going to say the same thing when we're doing antiderivatives, nothing's changed, is I do think it is helpful to rewrite this as cosine x, and then instead of sine to the 5th x, if you write it as sine x to the 5th power, which is what it is, I think it's much easier to then determine, oh yeah, that's going to be my baby. And now, if our u is that sine x, then what is our du? It's going to be cosine x dx, which again is totally what we needed. Let's go to the next slide and solve this guy. So I'll rewrite it. Our u was that sine, our du was that cosine, which was conveniently exactly what we needed. Integral, the cosine x dx, we're going to replace with the du, and then we have u to the 5th power. Take the antiderivative, we're going to add 1, divide by what we added, plus c, since it's an indefinite integral, so 1/6 sine to the 6x, or you can write sine x to the 6th. Either one is fine, they're interchangeable, plus c, whatever floats your boat. Okay, now we have one with an e, and I've picked up on these are a little bit more challenging for a lot of people, so let's break this down. So in some of the problems we've been seeing, ones that were like the integral x 5x squared plus 3 to the 5th power dx. Even the last one we just saw, integral cosine x sine x to the 5th power. We were taking whatever was in this base, right? And that was our u. And now when we're doing these e functions, it looks a little bit different. And that's because these are really compositions of functions, right? If we have f of g of x, our inside function is the 5x squared plus 3. And then what are we doing it to it? We're taking it to the 5th power. In this one, our inside function is sine of x. And then what are we doing to it? We're doing it to the 5th power. But now in these e ones, say we have just e to the 5x dx. You saw that in your ed puzzle. What is the base function? The base function is e to the something, because that's how the e function is. It's e to the something, versus these ones were something to the 5th power. Both of these were something to the 5th power. So what our baby is going to be different in this guy, okay? So just keep this in mind, that our e function is e to the something. If we did a composition of functions in this one, The 5x is our inside function, and then we're doing e to that 5x, right? So the 5x is our inside function in that one. Okay, so now let's do this problem. You see e to the something. So our u is going to be that 10x squared plus 8. And our du is then going to be 20x dx. And then do we see a 20x dx? No, but we do see an x dx. So let's go ahead and divide both sides by 20. So we have that x dx that we want to sub in for. Let's go to the next slide and solve it. Okay, I've just gone ahead and written what I had in the last slide so that we can solve it, because this is where we were at. So we were going to replace this x dx with the 1/20th du. So let's go ahead and do that. And then our u was this 10x squared plus 8, so we can rewrite e to the u. Let's take the 1/20th out. And remember that the antiderivative of e to the u is e to the u. Very important. Don't go adding 1 on that one. The derivative of e to the u is e to the u. The antiderivative of e to the u is e to the u plus c. So our final answer, 1/20th e to the 10x squared plus 8, because that was our u, plus c. Now let's do a couple of these u subs with some bounds, just so we remember how to do those. So in this one, hopefully it's obvious that this is our u. So our u is going to be 3x squared plus 1. Our du is going to be 6x dx. I don't see a 6x dx. I actually see a 12x dx. There are multiple ways to do this, but I'm just going to say, why don't we multiply both sides by 2 so that I have 2 du is 12x dx, and then I can conveniently replace it. Alternatively, of course, you could have, solved this for just x dx and said 1/6 du equals x dx and plugged it in there, and then you would have had 12 times 1/6 du, which is 2 du. We would have wound up in the same place. So there's always multiple ways to do these problems. I'm just going to stick with what I was thinking. So at this point, I'm ready to go to u's. I'm ready to go to all u's. I'm committing to all u's. You can't mix match u's and x's, all right? So if I'm committing to u's, then I need to change these bounds because these were x bounds. If my x was 0, then what is my u? My u is going to be 3 times 0 squared, which is 0 plus 1, 1. If my x was 1, then my u is 3 times 1 squared, which is 3, plus 1, which is 4. My new bounds are going to be 1 to 4. I'm going to replace the 12x dx with 2 du, and then I have u to the third power. So now I'm going to just take that 2 out. The antiderivative, I'm ready to take the antiderivative, add 1, divide by what I added, and our bounds are 1 to 4. I don't need a plus c because it's not an indefinite integral. And now I don't ever need to go back to x's because these are my u bounds, so I must keep this u. That's really important. Okay? If you have u's, just stick with u's, because if u changes back to an x and you need to change your bounds back to the x bounds, you have to stay consistent. You have to remember that these are u bounds, so that must be a u there. If you're going to change this to an x, you need to change back to x bounds, and why would you want to do all that extra work? That would be ridiculous. Now, 2 times 1/4 is 1/2. And then I'm going to go ahead and plug in. So I have 4 to the 4th power minus 1 to the 4th power. You can actually leave your final answer like that or keep going. 1/2, 256 minus 1 is 255 over 2 is our answer. But again, if you left it like that, golden. You can leave it like that for the AP exam. All right, now we're getting into some FTC on this one because I'm doing a derivative of an antiderivative, and that's my only bound that is a variable. So that's all I'm concerned about putting in and then chaining. Derivative of the antiderivative brings me back to the function itself. Plug in that x, and then we would chain that, but that's just the 1, so you don't really need that part, right? The answer is just cosine x to the 5th. The constant is going to drop off. Derivative of a constant is 0. Let's go ahead and do this one. So this is our only bound with a variable on it. Again, I only do this because I'm doing the derivative of the antiderivative. If I was just doing an antiderivative, got to do what I was doing, right? But I'm doing the derivative of the antiderivative. So go ahead and put that in there. So I have 1 plus x squared cubed, and that whole thing I need these parentheses. They're vital to getting a correct answer, all right? And then I'm going to chain it. So that is times 2x. And remember, you're chaining the bound because you're plugging it in first and then taking the derivative. To prove that, let me just show you. If I have, let's say, some constant to some x squared of f of t dt, and let's make that our g of x function, then what is the derivative of this? We know from FTC that it should be plug this in, because we're doing the derivative of the antiderivative, brings us back to the function itself, plugged in, f of x squared times 2x, but let's prove to ourselves one more time why. If I'm just doing the antiderivative, let's do that first. The antiderivative of little f is big F of t, evaluated from some constant to some x squared, right? So now we get big F of x squared minus big F of c. If we take its derivative, which is our goal here, the derivative of big F is little f, leave the baby inside, because this is a chain, times 2x. And the derivative of big F of c is a constant. So that's just going to give us a number. When you're evaluating a function at a constant, we just get a number. So that's why it drops off. So that is our proof of the FTC yet again, and why we're chaining this bound. It's because we plug it in first and then take its derivative. Now in this problem, I have bounds on my upper and my lower bound that are variables. So I do need to do a subtraction on this one. So let's go ahead and put the x cubed in first. 5x cubed squared plus 2. And then we need to chain it times 3x squared minus, now put in the x, 5x squared plus 2. And then to chain the x, that's just the 1. You don't need to write that. All right, we're almost at the end of this lesson. Let's close out by looking at an actual free response question that we can do all of. Very importantly, they tell us that the g of x function is defined by the integral from 1 to x of f of t dt. So the accumulator starts at 1. And here is a graph of f. So on this slide, let's just do part A. So part A says find g of 2 first and then g of negative 2. G of 2, so if g of x is this, then g of 2 means put in a 2 for our x, right? So g of 2 is an integral from 1 to 2 of f of t dt. We just plug in the 2 for the x, because our x is our 2. 1 to 2 of f of t dt. And this means our area under our f curve from 1 to 2. Okay, remember that 1 is our first bound. We're pretty much, this is saying what is the area of this little triangle right here, which the area of a triangle is easy, 1/2 base times height. But what is the height of this? They don't give us the y coordinate here. So we're not positive and we need an exact value. But you'll notice the slope here, right? This point right here is down 1 and it's over 2. To get from this point to this point, what are we doing? We're going down 1 over 2. Meaning this point right here must be down 1/2 over 1, right? Because the slope is negative 1/2. So that point right there must be 2 negative 1/2. So the area of that triangle, I'm going to do negative because it's below the x-axis, negative 1/2 base, which is 1, times height, which is 1/2. And so our answer is negative 1/4. Now, they also asked us g of negative 2. And that's going to be the integral from 1 to negative 2 of f of t dt. And of course, we usually like the smaller bound to be on the bottom. So let's just flip this and take the negative, which we are allowed to do. And now this is going to be the area under the curve between negative 2 and 1. And so it's going to be this. This triangle part is 1/2 base. Our base is 1. Our height is 3. And then minus, because it's under, and it's a semicircle, so half of the area of a circle, 1/2 of the area of the circle is pi r squared. Pi, radius in this case is 1 squared. So we just have 3/2 minus 1 squared is just 1 pi over 2. And oops, I forgot about the negative, which is critical. So we have to multiply the whole thing by negative 1. The opposite of that. You could leave this as your final answer, or you can multiply it through, and so then that would be the pi over 2 would be the positive 1, and the 3/2 would be the -1. So that should be our final answer there. Now in part B, they're asking us to find g prime. So if g of x is the integral from 1 to x of f of t dt, then what is g prime? By the fundamental theorem of calculus, it is just the function itself. So I think that part B is going to be pretty easy to find g prime of -3. What is g prime prime? The derivative of f of x is just going to be f prime of x. So they're asking us something about the slope at this point. So let's do g prime of -3 first. So we said that's just equal to f of -3. And so this is our f curve. We know f of -2. And then let's see, our slope is going to be down 2 over 2. So our slope here is simply 1, right? So that would make this point right here, -3, 2. So f of -3 is simply 2. And then when we want to do g double prime of -3, that's equal to f prime of -3. And that just means the slope at x equals -3 on the f curve. And so at this point right here, what is our slope? Well, we just had figured that out to do that last problem. And so the slope is just 1. And that's our answer to that part. If they had asked us, g double prime of, let's say this point here, 2, f prime of 2, of course, that's the same thing as asking g double prime of 2, which is how they would have asked it to us. Then we had found that this slope here was -1/2, remember from before? So that would have been -1/2 if you were looking there. And then if you were looking somewhere on this interval, it would be a lot more difficult unless they were asking you at 0. But anyway, that's how you do that one. Now let's try and tackle part C. Find the x-coordinate of each point at which the graph of g has a horizontal tangent line. So g has a horizontal tangent line. We want to be looking at where g prime equals 0, right? And what is g prime again? G prime is f of x by FTC. So g prime of x equals 0 is the same thing as where f of x is equal to 0. Where does that happen? That happens at -1 and at 1. So that's a good answer, and that's a good justification. For each of these points, determine whether g has a relative max, relative min, or neither a max nor a min. So g has a max when g prime goes from max positive to negative. And remember, g prime is the same thing as f. So that's the same thing as when f goes from positive to negative. At x equals -1, f changes from positive to negative. Therefore, we have a local max at x equals -1. At x equals 1, which is the other one we're looking at, f does not change signs. Therefore, g has neither a max nor min there. Okay, so x equals -1 was a max, x equals 1 was neither, because we have no sign change there. Final part of this problem says for -3 is less than x, which is less than 3. So on this whole interval that we see here, find all values of x for which the graph of g has an inflection point and explain your reasoning. G has an inflection point when g double prime changes sign. Now, what is g double prime? Break it down again. G was the integral. G prime was simply f of x. G double prime is f prime of x. So this is the same thing as when f prime changes sign. When does f prime change sign? Well, f prime is positive when f is increasing. F prime is negative when f is decreasing. So that happens when f changes from increasing to decreasing, or f decreasing to increasing, which of course is the local maxes and local mins on the f graph. And so that happens at x equals -2, at x, don't forget about this one here, that one's an easy one to miss. So here, here, and here, x equals 0, and at x equals 1. They said explain your reasoning, and we already did explain our reasoning here. They're going to be looking for when g double prime changes sign, when f prime changes sign. You need to say when it changes sign, not just when it equals 0. When it equals 0, it's not sufficient, right? It's just like what we determined in this one right here. It can equal 0, but we didn't have a sign change, so it wasn't a max or min. It's neither. Don't forget, equaling 0 is not sufficient. We need a sign change. So to wrap things up, we're going to do one more question, which is tricky at first, but once you get the hang of it, these really are no more difficult than the types that we've been doing. So this is from your homework 5.5, number 51. And so what's tricky about this, let's go ahead and do what we normally would do in this one and identify the u and the du. So I'm going to rewrite it as I have been, the integral from 1 to 2 of x minus 1 to the 1/2 dx. So it's very clear there that my u is going to be the x minus 1. If our u is our x minus 1, then our du in this case is simply dx, because the derivative of x is just 1. Now, the problem is that's going to take care of this dx, but what about this x? Right? I said if we are going to use, we got to go all in. We got to switch everything to use. So we got to switch bounds. We got to switch this to a u. We got to switch this to a du. But what about this x? What are we going to do with it? Let's go ahead and do what we know we can do and do the bounds first, because our x bound was 1, and that's going to mean u is 1 minus 1, which is 0. And when our x is 2, that's going to mean our u is 2 minus 1, which is 1. So our new bounds are going to be 0 to 1. And we said we're going to replace this with a u to the 1/2, and this dx is simply our du. However, what is this x? So let's look down at what we have. We know that u is x minus 1. So what is x? What if we added 1 to both sides? U plus 1 equals x. Okay, we just solved for x. X could be replaced with u plus 1. Now you might be thinking to yourself, I feel like I just went in a circle. What's the difference between that and that? I have 2 terms multiplied and I still have 2 terms multiplied. The difference is this I could not simplify, right? But this I can distribute now. I can distribute that because I don't have it all under that square root anymore. And so that's the difference. Now I can multiply this out and I get the integral from 0 to 1. U times u to the 1/2. Same basis, add the exponents. So 1 plus 1/2 is 3/2 plus u to the 1/2. And then take the antiderivative. So add 1, flip it, plus add 1, 3/2, flip it, evaluated between 0 and 1. I'm just going to take it down here so I have a bit more room. So plug in a 1 everywhere first. So we have 2/5. 1 to the 5/2 is just 1, plus 2/3. 1 to the 3/2 is just 1 again, so I just have 2/3. And then when I put in the 0, I just get 0 plus 0. And so my common denominator would be 15ths. So I have 16/15 as my final answer. You could have actually left your answer right here. That's fine. 2/5 plus 2/3 would have been a fine answer also. But that's about it. So hopefully once you see this type of pattern, these problems become easier. The key thing to remember is that once you go to use, you got to go all in. You got to go all use. That means you got to go bounds use. Every single thing has to be a u. You can't mix and match the u's and the x's. All right. That's it for this lesson. Bye.